Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Miller, and I'll be your host for today's presentation on 3D accelerating electromagnetic simulations with machine learning, an introduction to EMA3D Connect. Please use the Q&A feature to submit any questions you have during the webinar. At the end of the webinar, we will address any submitted questions. Our speaker for today is Parker Renicky. Parker is a software developer too at Electromagnetic Applications, where he leads the new EMA3D Connect group that focuses on visualization, collaboration, and AI ML. He aims to build machine learning models for numerical simulations that deliver order of magnitude speedups, revolutionizing how complex physical systems are analyzed and optimized. Parker joined EMA in 2023 and has been contributing to development, operations, software testing, and API development. Without further delay, I give you Parker.
Thank you, Matt, for the introduction, and thank you for everyone joining today. So today, our webinar is about accelerating electromagnetic simulation with machine learning. So an overview of this webinar, I'll kind of go into an introduction about what EMA3D Connect is about and the problems we're trying to solve. And then I'll go into how we're applying machine learning to electromagnetics, and then the end-to-end framework that we built in order to allow you to generate data, to build and train these machine learning models, and to deploy them into an environment. So traditional challenges in simulation workflows, a lot of times it can be costly to do optimization studies and to analyze the design space. And usually it's very hard to integrate all of the data that an organization might have in order to implement machine learning, which can in turn cause budget overruns when developing products. So why machine learning with electromagnetics? Well, traditional simulations are time expensive and costly, as all of y'all are aware of. And what machine learning can do is allow us to run these simulations in seconds, enabling rapid iteration and design exploration. And it can go farther than that. You can integrate real data from your product as well, integrate low fidelity and high fidelity simulation data, and kind of build a model through the product, through the life cycle of your entire product. And what it also allows you to do is have real-time assessment. So since simulations are so costly and they can take hours or even weeks to run, doing inference on a model can take less than a second to minutes to predict exactly what a numerical solver would take hours or weeks to do. So the key components of EMA3D Connect, the first thing is we need to generate the data, right? And so the unique position that EMA is in is all of the machine learning that we're doing right now is with simulation data, and we have numerical solvers, so we can generate that data. So then once we have that data generated, we need to understand how to process the data in order to put it into the machine learning model. And while we're doing that, we build and train the models. And once we have the models trained, we'll do the deployment and the version control, and then actually being able to visualize the results, whether it's from traditional numerical simulation or from the machine learning models that we built. So what is a surrogate model? So really all a surrogate model is a data-driven model to predict your simulation results, right? So it's the machine learning model that's trying to emulate the behavior of your numerical simulation. And there's surrogate models it's kind of a new word, but it's been done lots of times with sensitivity analysis, reduced order models. But really what the modern surrogate models here are doing is implementing deep learning into the kind of ways of being able to analyze these models. So what we've been working on is building a surrogate model for shielding effectiveness. So what this model does is it predicts the shielding effectiveness given an EMC plus configuration file. And it enables order to magnitude speed up, so you can input your EMC plus configuration file, you can click run, and in less than a second you have the results for a given electrical enclosure. Now in this study we focus on shielding effectiveness, but these concepts can be applied to radiated emissions and radiated susceptibility as well. So here's the model architecture for it. I won't get too much into the details of this. If you're more interested in kind of the nuances and all the details of the architecture, feel free to reach out, and I have some supplemental material I can give you. But high level, the way it works is we take the finite difference time domain, we reduce it to encompass just the mesh of your enclosure. It incorporates the illumination angle and the material properties, and then it goes through layers of a graph neural network and eventually through fully connected network to predict a range of your shielding effectiveness over a range of frequencies. So the model input for this is, like I said, it's the FDDT domain where it's just the voxels of where the material is defined. And so you can see in these pictures here, this is in ANSYS Discovery, so you can set up your simulation in ANSYS Discovery, generate your configuration file, and you won't really see this point cloud, but kind of under the hood, what's happening is in the pre-processing steps, we're generating this point cloud to eventually be able to get it into a format and into a graph representation that the machine learning model can ingest and utilize GPU acceleration. And so what we do with this mesh is from the top to the bottom, there'll be different amount of points in the resulting point cloud depending on your enclosure that you do. So we subsample to a constant amount of points, and then to incorporate artificial edges into this point cloud, we do a k-nearest neighbors algorithm based on the Euclidean distance of the points. And we also encapsulate the illumination angles and material properties from this configuration file. And these properties are incorporated as global level features, right? So the point clouds you can consider as nodes on a graph, whereas the illumination angles and the material property is graph level features or global level features. And so that's some of the challenges here, was incorporating different, you could call them features, to be able to make accurate predictions. So here is the model output. So you can see on the left here, there's just example electrical enclosures. And so on the right, you can see the orange line is the actual shielding effectiveness from the simulation result, and the blue line is the predicted shielding effectiveness through the result. So a little bit more information on how this works. So a lot of times when you set up these simulations, to be able to resolve different aperture sizes, you'll have different cell sizes in your simulation, and which results in different frequencies that you can resolve. So the way that we handle this is we store as metadata into each training sample the maximum resolvable frequency that the specific simulation can do, and the model is trained over the largest frequency in the data set. So let's call it maybe 13 gigahertz. And then the model below, you can see the maximum was 10 gigahertz. So any frequencies that are kind of generated artificially for the model after 10 gigahertz are just masked and not used in the training process. And so this kind of gives you flexibility to be able to use the same model to analyze different kinds of enclosures, right? And as you build kind of a database of additional enclosures, you can retrain the model and kind of have um, a single model that encapsulates all the types of enclosures and can support you for the life cycle of your product. So once we have the model trained, how do you deploy this model, right? So there's a number of ways you could do this. So what we've done here is we've created a demo application that allows you to run inference on your model. So what you can see here is you can upload your EMC Plus configuration file. It shows you the point cloud, and then you can click run, and within less than a second, you get the results of your the shielding effectiveness results. In this point cloud you see here is actually this bottom electrical enclosure with the exact same configuration and illumination angles and material properties you see on the plot sample 42 here. So this, this is just a demo app. We can through a web UI, and it's deployed through a Docker container, so you can deploy it. But that's just one way you could do it. There's lots of different ways we can help you deploy and visualize not just machine learning, but also your simulation results. So a little bit into the end-to-end framework. So really the hardest part of generating these is, not just coming up with the model architecture, but being able to generate the data and understanding the data, right? So we've kind of created a framework that involves data. Then once you have your data, you do the training. Once you have the training, you do the deployment. And then ultimately, you need a way to visualize the results, which you can do through UI, through the current ANSYS Discovery tool, or through ParaView, or NVIDIA Omniverse. So we've kind of built this framework to accommodate numerous requirements for customers. So a little bit into the generating the simulation data. So the way that we do this is we use ANSYS Discovery and the APIs and EMC Plus APIs to generate different combinations of the model, right? So we'll change varying illumination angles, we'll change size of apertures, the width, length, and height of the box. We'll go and grab different types of enclosures, and we have an API script that allows us to generate the EMC Plus configuration files. So once we have this and we have a good distribution of configuration files, we queue this into EMA's cluster using a workload manager. And so what this allows us to do is queue up our simulations and kind of just let them run on the cluster until we have the data generated. And while we're generating this data, really the important part and the big thing is understanding how your data lives in terms of what's the structure of your data, so you can decide how you should build the pre-processing and how you should build inductive bias into these models in order to create something that generalizes well. Because an issue that we have in kind of ML for physics is we don't have the luxury of downloading the web archive and all the different web pages available to us to have petabytes of training data like you've seen in large language models. So it's a big challenge is being able to generate high quality data that allows our models to predict accurately. And furthermore, we'll never really get to the scale in terms of the data available that large language models have. So it's very important, especially in machine learning for physics and creating these surrogate models, is to find clever ways to build prior information and inductive bias into these models so they can generalize better with less data. So this is kind of a picture that I think is really helpful, and it's called the 5Gs of geometric machine learning. And it's kind of a framework that I use to decide what type of model architectures based off of the data and the data symmetries that the data possesses. So in our case, for the shielding effectiveness model I showed you, is we eventually put it into a graph representation, right? And so what a graph representation has, the symmetries it has, is permutation invariant, right? So in the model architecture, you need to do permutation invariant operations. And that's really kind of the crux of a graph neural network. And it allows us to be able to make better predictions with less data. Now, when we started this, we started with a grid representation because naturally a finite difference time domain sits on a grid. Well, there's challenges, I won't get into it too much, that possess with a cursive dimensionality, where if you try to incorporate everything into a grid, it's the size of the input just becomes exponentially large. And so with graphs, we can be really clever with the way we incorporate simulation data into it. We can also incorporate non-uniform meshes like FEM meshes. You can add edge features, node features, graph features. So you can just really be clever with the way that you represent your data. A little bit more into the pre-processing. So the framework we've created here is creating pre-processing that doesn't work just for training, but it also works for the production environment. So the pre-processing is kind of in a single source of truth, where if you want to add additional feature, for example, in the shielding effectiveness, we have the illumination angle, we have the material property, but maybe there's some sort of other feature, maybe eventually incorporating seams as edge features into these models to encapsulate that as well for a more complicated model. You can kind of change the way that you pre-process your data to turn it from the EMC plus configuration file to a point cloud, eventually into matrices of numbers, which is an adjacency matrix that allows us to represent a graph and do GPU accelerated learning on these models. Yeah, so I think this is a really important part, because if you don't have the pre-processing in place, it can make everything challenging and messy to deal with. So once we have these models trained and deployed, you can package them up in different ways, right? So that we right now we support a couple deployment options, but we're not constrained to this. I think being able to Dockerize and containerize the model or the application is easy, because it packages all of the dependencies that you need to make the model work. So all you have to do is run the container image to be able to do inference on these models. And another part of this is, once you train the model, it's not just a one and done, right? You're going to be using this, you're going to be generating more data, doing more simulations. So it's a feedback loop, right? So there'll be multiple versions of these models. So we need some sort of model registry to version and to deploy these and to test them. And so we can support that as well, being able to train the model for you. And then once we have additional data, we can fine tune it on the new data and then push the new version. And you can simply just pull the new model from the model registry and use it. And another thing too is we support hybrid cloud. So you can deploy this on the cloud, or you can deploy it on-prem on a local Kubernetes cluster, on bare metal, on something like NVIDIA Triton Inference Server. So there's lots of different options that you can use to deploy these models. So visualizing results. So we have a couple different ways, and you've seen some of them so far. I showed you the custom app, which you can, for the model, we can build a visualization tool that just allows you to easily see the point cloud and see the shielding effectiveness and whatever other model we might be building. It could also be for visualizing traditional simulation data. So one thing that we try to stick to is the input and the output of these models are always representative of the way that our EMC Plus and Charge Plus generate the data as well. So we try to keep it in a similar format. So whether you're using the machine learning or you're using EMC Plus or Charge Plus, the way that you can visualize the results is the same. And so with the custom apps, we keep that, we kind of keep that method, and we also support a pair view plugin, which I'll get in showing you a video here in a couple slides. And we've also started to support NVIDIA Omniverse, utilizing a pair view and Omniverse connector that allows us to do photorealistic renderings with real-time ray tracing technology. So here's our pair view plugin. You can see for this example, it is an HDF5 file, which is just the 3D probe. It allows you to just upload the HDF5 file, and then the pair view plugin will recognize that it is an HDF5 file and ask you if you want to use the EMA3D plugin to render it. Once you have it in, it lazy loads the time steps. So it doesn't load them all into memory. So you can upload massive HDF5 files for 3D visualizations here. And what you can also do is upload any sort of CAD files that you might have and overlay it, and you can scale the HDF5 file to fit the geometry as well. And we don't just support the 3D probe, we also support bulk data probes and other types of simulation results from EMC Plus and Charge Plus here. And so you can see here, I'm uploading an STL file with the simulation results, and this was a radiated emissions demo that we have here. You can see now we have the 3D results. You can scale it how you want, analyze the results, and I think the real power of this is the filters that you get with pair view is very, very powerful. So it allows you to import the results from our solvers and utilize the decades of work that has gone into building the algorithms behind filtering and post-processing of your simulation results. So here is a Omniverse demo. So this is an ESD demo here. So what we do here is we do all of our post-processing in pair view, and then we have a pair view Omniverse connector. And once we have it in Omniverse, it allows you to do these photorealistic renderings here. So yeah, that's how EMA3D is implementing machine learning into numerical simulation. And I think this will as we develop these, this can really enable faster evolution of design and enable us to explore a design space in a more complex design space than traditional reduced order modeling gives you. You'll be able to look at maybe features. The machine learning model will be able to find features that were kind of otherwise impossible to really capture in traditional reduced order models. This, like I said, this case study uses shielding effectiveness, but this approach can also be designed to work with radiated emissions or radiated susceptibility. So yeah, EMA3D can build similar models for your products and designs.
All right. Well, thank you, Parker, for that very informative presentation. I want to remind everyone that there's a Q&A feature at the top of the webinar interface. We already have some questions coming in. Feel free to submit additional questions during this Q&A period. Before we get into the questions from the audience, Parker, I had a couple of comments or questions for you. I know in some of our conversations with some of our DoD customers, they're really excited about this technology. And one of the things or reasons they're excited is that they have existing measured data for some of their platforms, and they would like to combine that with simulated data from our tools like EMC Plus and Charge Plus. Can you speak to that for a moment in terms of the ability to use a combination of measured and simulated data?
Yeah, definitely. So I think that is one of the real powers that we can get out of machine learning is not just being restricted to low fidelity and high fidelity simulation data, but also being able to incorporate physical test data into these models. So what that would look like is we would start with the low fidelity data, right, when we're building the model to get started, because EMA has access to that. We can start to train, design, and develop the model. Then once we're happy with the direction the model's going, we can start to add higher fidelity data into it. And once we have that, and we're implementing this for existing platforms, or we already have the existing data, we can incorporate that into the model as well, right? And so for the example in the graph neural network and the shielding effectiveness model, what that might look like is if we have certain simulation data, maybe we know where it is spatially, it might be a global feature that we can implement. We can add that simulation with that real experimental data and even give it a higher level of importance in the training, similarly like how we implement the illumination angles into the model. And so, you can really kind of generalize the way you think about this is, in terms of building machine learning models on 3D data, you kind of can have node level features, you can have edge level features, and you can have graph level features. And you can predict graph level features, you can predict node level features, you can predict edge level features, right? And it can be classification, right? A yes or no answer, a continuous value like regression for shielding effectiveness. And yeah, so that's kind of how I would envision being able to build real data into these models.
Okay, yeah, thank you. Yeah, I think one of the reasons our DoD customers, and this certainly is not just for military, I mean, you could use the same sort of analogies for consumer electronic products or automotive products or a wide variety of applications. But one of the reasons our customers are excited about this is that they can get these really powerful and fast simulation capabilities into the hands of non-experts. So you don't have to be a 20-year veteran with a PhD to be able to generate reliable simulation data. And you can very, very quickly assess different threats or different scenarios to a platform. So it's, again, a lot of excitement from our customers about this capability. Other question, or I guess one thing I'd like you to walk through, because the first time I saw some of the shielding effectiveness results, I had to kind of scratch my head a bit and understand what was going on there. So, you show that really great comparison between the full EMC plus simulation for the actual configuration and then the very fast solution generated by the ML models. Can you walk us through a little bit about the training data that you used to generate that model? Because I believe what you did, and correct me if I'm wrong here, is that you considered a lot of different scenarios with different aperture shapes and locations and things like that. And that is what you used for the training data to generate that ML model. Is that correct, or can you explain that better than I just did?
Yeah, no, that's correct. So what we did is we took electrical enclosures that are of similar size. So like, I think the smallest enclosure we did was like an Arduino or Raspberry Pi enclosure, and the largest we did was like a GPU super case, right? And they kind of have all varying sizes of apertures, for fans, for airflow, for cables and harnesses. And we just kind of grab them all over and from our existing database. And what we're working towards is kind of building a data set of these enclosures that we can ultimately use for the pre-training of customers' data, right? So we can build kind of a foundation model with this data. But yeah, so what we did is we just kind of had 20 to 30 different types of apertures or electrical enclosures, and then we for each of those enclosures we changed the illumination angle, different, just kind of 6 different areas, right? So kind of each angle of attack, I guess you could call it. And then for the material properties, we did an aluminum, a stainless steel, and then a carbon fiber. So kind of, a very high conductivity, more middle, and then one on the lower side, right? And so for each of these CAD files, we were able to generate around 40 different combinations of the other features. So once we had this, then we kind of have our data set that we can do our pre-processing on. And I kind of want to reiterate, I think it's really important for us to continue to build this data set, right? This is our initial data set. Now that we have a baseline, we'll continue to add more and more onto it, right? And we'll have a foundation model. And so when a customer comes to us and says, hey, we want you to build one for us, we can use the data that we have for the CAD files on top of the data that we have for our customer, right? And so we can keep our customer's data for that customer, obviously, right? But we also have kind of the foundation data set that we can use to get more information, because more data, the better when it comes to these models.
Excellent. Okay, thank you. Yeah, so if I'm working for a consumer electronics company or maybe a military avionics company and I've got a shielding effectiveness requirement for the enclosure, then with this tool I could go through and very quickly consider lots of different scenarios and almost instantly have those results. Am I understanding that correctly?
Yes, exactly. Right.
Yeah.
So you can use the model. We can pre-train it on whatever data you have. You might not even have any data, right? We'll have a foundation model, and we're working towards on being able to have lots and lots of different CAD files. So you might be able to get results even if you don't have any data, at least to start, right? And it's, you can't think of it as a one stop and shop. It's a life cycle of your product. Start somewhere, and once you get the data, we can retrain it with your data and just get it to work better and better for your specific use case.
Okay, very good. So we have some questions from the audience here. First one, what are the main challenges you see with traditional electromagnetic simulation workflows, and how does machine learning address these?
Yeah. So the main challenges I see is the time it takes to run these simulations. Now, we've come a long way, obviously, with being able to simulate something in a computer versus having to build it and test a prototype. But now, with the era of AI, it brings us into, I think, a new age where we can rapidly accelerate the design process, right? So, like I said, a lot of times being a developer, right, when you're building something, when you're doing something, having a quick feedback loop so you know what mistake you did or you know what you need to change as quick as possible, and then be able to execute on that change to get the results, right? So maybe, for the shielding effectiveness, you can do it in under a second. So you could do hundreds of designs probably in a single day and get an idea for what type of changes you need to make instead of having to go through the pain of running 100 simulations and then a week later coming back and deciding on what change you need to make. So I think the biggest value in machine learning is you can amortize the cost of generating the data, but once you have the data and you have the model, it can really reduce that feedback loop for engineers.
Okay, fantastic. Thank you. What is the difference between the traditional reduced order model and the surrogate models you are showing us?
Yeah, so traditional reduced order models is really just specific parameters, right? So what you're doing is, you might have an aperture size, a box size, height and width, and you have illumination angles. And so it's kind of like a parametric study, right? Where you're looking at for each input, for each random variable, which could be your, all the parameters I just mentioned. How does that change how sensitive is that to the output? In this case, it would be shielding effectiveness, right? Once you have that, you can build kind of a response surface and then be able to do something similar to what the surrogate model in terms of being able to predict based on pure parametrics, right? But those models don't incorporate kind of spatial aspects of the 3D geometry, right? And so it's purely trying to predict what the results will be given on the change of your inputs. Now, where deep learning and more specifically graph neural networks and the studies that I've been doing come into play is these are non-parametric models, right? We give it the CAD file, we give it the point cloud of the geometry, and instead of learning just the width and the height and how that changes, it learns all of the spatial features of the specific aperture, right? And these models aren't 100% interpretable, but it allows us to capture a lot more complex features and characteristics of how the geometry and how the illumination angles and material properties come into play when making these predictive models, right? And so that's the real difference between traditional reduced order models and deep learning models, is that it's parametric versus non-parametric, right? We can try to learn on 3D spatial data instead of it just being kind of parameters we pick and choose from, right? Like there might be some sort of abstract feature in the geometry that the human mind would have never thought of, right? And these deep learning models can kind of capture those types of hidden features.
All right, thank you. Last question that we have so far, and again, remind everyone there's the Q&A feature at the top, so if you do have a question, don't be shy. Please ask those questions now. So last question we have is, why is the finite difference time domain reduced? In other words, why don't you represent the entire FDTD as an input to the model in your demo?
Yeah, so in our initial study, we started to represent the entire FDDT domain into the model. But as we tried to scale it up to more realistic enclosures, you run into the curse of dimensionality, right? So as you increase your domain, the trying to incorporate all of the information into the machine learning model becomes intractable very, very quickly, right? Especially if you have maybe 9, 10, 11 features per voxel or per cell in your finite difference domain. So we had to kind of work a way around this, right? And so that's when I went from representing the data as a grid, right? And grid have kind of translation invariant operations, right? But you can't just pick and choose what you want. You have to, if you have a 256 by 256 by 256 grid, you need to encapsulate all the data in there. You can't just remove a single voxel inside of that. So what we did to reduce the size of the input is transform our data from kind of a uniform grid to a graph representation. So now, instead of encapsulating all of this kind of sparse information, right, because most of the characteristics of shielding effectiveness is not necessarily from kind of the the permittivity and permeability of free space somewhere in our domain. It's coming from the illumination angles and most importantly the geometry of the enclosure. So what we did is we read the EMIN file or the EMC plus configuration file, and it selectively chooses the voxels that have material properties defined in them. And then we construct this point cloud, right, from the configuration file to only incorporate the voxels that contain useful information, right? And we encode the positions of each vertice in the voxels as features. And one of the important parts is in order to in order for the machine learning model to know kind of and understand the positions, we do relative distances between each point, right? So that's one of the things of kind of permutation invariance is, you can change the coordinate system now of your original domain, and the machine learning model will produce the same results because when we're doing these edge convolutions in the neural network, it's looking at relative distances between its k nearest neighbors, right? And so this allowed us to scale up the model from just kind of simple, small, coarse boxes to higher fidelity, realistic models.
Okay, thank you. All right, well, I believe that is the last question. If any additional questions pop up here as we're wrapping up, we'll ask those as well. Parker, can you go back one slide where it shows our email addresses?
Sure.
Yeah, so just a reminder, if you want to do a quick screen capture here, and we'll also be emailing you after the webinar with a copy of the recording of this presentation. But feel free to reach out to any of us if you have questions about the technology. We do provide, as Parker talked about earlier, consulting services, so we're available to develop models for your company or organization. Or if you just have general inquiries, again, don't be shy. Please reach out to us with your questions. So the next webinar in our series is going to be leveraging test and simulation to de-risk certification, and this is specifically for the aerospace industry. That presentation will be given by Justin McKinnon on December 4th. Justin is a designated engineering representative for the FAA and an EMA employee. So there's a lot of great knowledge and real world experience that he'll be talking about in that webinar. And in closing, thank you for your time and attention today, and I hope you have a great rest of your day.